My name is Priya Natarajan. I'm an astrophysicist and at the faculty at Yale in the departments of astronomy and physics. I am also currently the director of Yale's flagship interdisciplinary program, the Franke Program in Science and the Humanities. And it is my real pleasure today to set off a new series, a themed series of questions about the nature of inference, understanding the nature of inference, trying to discern the role of causation, correlation, these sort of deeper questions that are very, very important to really disentangle. And so this is a series that is supported by some funds from the John Templeton Foundation. And what we are going to do as part of this series is have a multidisciplinary exploration on the question of inference and how inference, how we infer in different fields, philosophy, computer science, physics, biology, organizational behavior, how we actually build conceptual models. And these can be models that are either numerical, computational, and how we make inferences. So, and as you all know, there's a bit of a bandwagon right now with machine learning and big data and so on. But one of the key sort of deeper issues that isn't resolved yet, and machine learning aspires to get there, is really helping disentangle causation and correlation. And fields like physics have a lot to offer because we have this grand architecture of physics laws of physics that govern cause and effect and help us therefore figure out and discriminate between causation and mere correlation. So speaking to this question and talking about the deep roots of understanding causes and effects, we have a wonderful speaker today inaugurating our series, and that is Carlo Rovelli. And before I give a wonderful gushy introduction, because I'm a great admirer of his work, his writing, and his thinking, I just want to give a shout out to our benefactors, Richard and Barbara Franke, who I hope have joined us today. Thanks to their generosity at the Franke program, we have been able to run these wonderful events, and we have not allowed the pandemic to scupper our enthusiasm to explore things intellectually. Thank you very much. And I also want to remind all of you that we are recording this event, and all participants must therefore mute their videos, as everyone seems to have done. And so the format of the talk is that Carlo will speak for about an hour, and then we open up to questions. And we will be managing questions through the chat. So please type in your questions in the chat, and then we will pass them on. We will, Ty and I will pass them on. And I just want to also say thanks to Dr. Ty Camp, who is the assistant director of the Franke program and has really helped with advertising and pulling this event as well as the series together. Want to give a shout out to many future speakers in our series who are there today. And I welcome you all. And thank you. And I think that the one other thing I wanted to mention is that following today's talk, we have at the same time a discussion with the same Zoom link that you can join tomorrow. And that would be sort of a follow-up, more in-depth discussion and a conversation between Carlo and one of our core project members, Dr. Eric Winsberg. So I invite you all to attend that. I promise you it's going to be a real double treat with today and tomorrow. Okay, so most of you, Carlo doesn't really need an introduction, but I love to give these introductions because it's just remarkable to see the life paths of people and the places that they have kind of inhabited, the roles they have inhabited to reach where they are now. So as most of you know, Carlo is a theoretical physicist who is very well known for his work on quantum gravity, particularly loop quantum gravity, and also the foundations of physics, questions and deeper questions about quantum mechanics, and overall sort of more generally interested in the history of ideas. So he's interested in the history and philosophy of science. And one of the things that has been wonderful for me to have found out about Carlo is that, he has this incredible expansive mind and has been interested in exploring sort of non-European sources of thinking, and rightly recognizing that intellectual work follows an arc, and there are many people who make contributions and offer sort of new insights. So we have recently talked about the work of the Buddhist philosopher Nagarjuna, who is a great fan favorite with both of us. So Carlo was born in Italy and graduated from the universities of Bologna and Padua, and he has worked in Italy, the United States, France, and Canada. Right now, he heads the quantum gravity group of the Center for Theoretical Physics at Marseille. He's a member of the Institut Université de France. He's an honorary professor at Beijing Normal University. And he's has honorary doctorates from the University of San Martin in Buenos Aires. He's a member of the International Academy of Philosophy and Sciences. His list of awards just goes on and on and on. So I will just sort of stop with just 1995 because it gets very thick and fast after that. So in 1995, he was awarded the Xanthopoulos Award for the best relativist under the age of 40. So he has, the remarkable thing about him is research papers, research monographs and books, like scholarly books on quantum gravity, published by Cambridge University Press, quantum covariant loop quantum gravity, published in collaboration with Francesca Vidotto in 2014. He writes research papers, these textbook type monographs, detailed technical monographs, and fantastic global bestsellers, amongst which, of course, it's hard for me to pick a favorite, but the 7 Brief Lessons in Physics, as someone who's written one book myself, I have to say I marvel. It's been translated into 44 languages. And my favorite recent book has been The Order of Time. It's just absolutely fascinating. So he's, of course, as you can imagine, included by many, sort of the top thinkers of the year, by many magazines and on many, many lists. So suffice it to say that today we have a speaker who is amongst the list of 100 most influential global thinkers. We cannot wait to hear from you, Carlo, what you have to teach us about what is a cause and why does it happen before the effect. And in his good characteristic style, he asks a very simple question, one that might seem obvious to all of us. At least we have made that assumption, and he's going to be demystifying it and showing us the various layers. So without much further ado, Carlo, take it away. And thank you so much.
Thank you, Priya, for this extremely generous and embarrassing presentation and introduction. I'm very honored. I'm very honored by the opening this series. I hope to be at the level. I certainly will not be at the level of what you're expecting me from this introduction and from this series, but I'll do my best. Let me share my screen. Yes. So as you just said, exactly, you gave the best abstract of my talk. I'm asking a apparently naive question: what is a cause and why it happens before the effect? Namely, I'm talking about causation, which is not about inference in general, of course. It's the specific causation, seeing as causation in nature. This process causes this other process. And I'm asking about the time ordering between the cause and the effect, the relation between the arrow that goes from the cause to the effect and the arrow that goes from from before in time to after in time. It's an issue which has been which is far from trivial, as you will see as I try to go into it, which has been puzzling me for a long time, and in fact, is puzzling many physicists, as I will argue. And there's a lot of philosophy around it, and there are a lot of different positions. And let me start by giving you the bottom line. the rival point, so to say. There are two sort of ideas about the source, the origin of the time orientation of causation. One is that it is in nature. This little picture here with the mountains, the moon, and the stars is going to be my icon for nature. And it's primitive. Namely, the way nature works is that there's a past, the past causes the present causes the future, and so on. So if we want to understand nature, that's the way it works. There is a direction of time, which is a direction of events causing other events. The opposite view, which it's perhaps at first less obvious, but is very obvious for a person who has studied theoretical physics, or physics in particular, is just there is no arrow of time in nature, and the relation between cause and effect has a direction from one of the two relata to the other, which is just what we project on correlations which happen in nature without any time order. So this little person here is my icon for we projecting on something. And what I want to argue is that my arrival point is that both these extreme views are wrong, in the sense that badly incomplete. And what we have to do to understand the connection between causation and direction of time is to go into details and discover that there is a very peculiar and very subtle dance between the two, the natural and the subjective, in a sense that I will try to be much clearer in the course of this, which is far from obvious, and which I believe science and physics in particular can help disentangle. Priya has used various times the word disentangle. I think is a proper word in this kind of context. We use ideas, we use notions, they are made by various pieces. We should understand where they come from. This is a plan of what I'm going to do. There is an original part, which is the intermediate one, in which I will present a couple of results that I obtained working on physics, especially in thermodynamics and statistical mechanics in recent years, which I think help adding one key piece to the puzzle of understanding causation. But before getting there, I will spend some time to give an overview of views about causation, explaining why there is a problem, what are the different perspectives that you find in the literature, from the classical literature to the current discussion about causation. And I will argue first that in science, there is nothing like time-oriented causes. And then I will argue for the opposite idea, that in science, there are all over time-oriented causes, and I will try to clarify in which sense both statements are correct. Once putting the various pieces together, I will conclude in the end by trying to give the overall picture. So where the notion of causation comes in, why do we use it, what it is in the way that we use it concretely in the sciences and in our everyday life. And I'll offer a tentative sort of overall picture. I will also add at the end a little coda about one further step of understanding sort of one of the layers of this construction, which is an idea of which I will be much less sure I can defend it all the way. It's an idea which I like, but I'm far from certain about it. So I want to distinguish it a part in which I'm giving a description of ideas which are in the literature, are a shorter part, which is my own contribution, a conclusion which I put all together, and then a part in which, unlikely the rest, I am less confident about everything. All right, let me go into it, and let me start by say, what do I mean by causation? And by causation, I mean what we usually mean by causation. So everything is the opposite of everything. We use the notion of cause in our life in a variety of different ways. When we talk about an event and we say, what is the cause of this event? The possible answer are the most different ones, right? Here is an example. The door of my refrigerator is closing now. Why? Because I'm pushing it, or all the possible ways of thinking what's the cause, because I'm picky, because I was troubled in my childhood by a very messy mother. So now I close all the doors. In the scholarly literature, the different causes has been analyzed since ever, in all the centuries, in all the geographies. And I think most people are more or less familiar, or at least have heard the analysis of the different causes which are in Aristotle. And as Priya was mentioning, there is a parallel very often in Indian thinking to Mediterranean thinking. There is a very parallel, in fact, slightly more refined version of the same breaking out of causation, which is in Aristotle, in Buddhist, in classical Buddhist philosophy. Now, what I want to say is that all this notion of causes are time-oriented, including the final causes of Aristotle and similar. I don't want to go into the explicit discussion on in which sense they are also time-oriented. If you want, you can ask a question about that. But the point is that in our use of the notion of cause, there is always a implicit assumption about the direction of time. Now, what are causes? How do we make sense of causes? In the literature, the literature on causation, the philosophical literature on causation is vast, and there's all sort of interpretations of what we mean by causes. So this is a list. I'm not going to the list. I'm not discussing them. Some of these ideas are going to appear in the later discussion. I just mentioned the two extreme positions in the last line, which is primitivism, namely a sort of a cause and effect are a fundamental notion we need to make sense of nature and what is going to happen. So we shouldn't break it up in something else. And to the opposite extreme, eliminativism, we can get rid of it. We just resolve it in sense of something else. To understand nature, we don't need causes and effect. And you will see how this comes in the discussion in a moment. And here I address not the philosophy of causation. I'm not a philosopher. And in fact, I put my hands ahead to the various philosophers in the audience, asking pardon for my naivety. I will mention philosophical idea in a naive way in which a physicist like me sometimes related to them. But I think philosophically, I'm a naturalist. I think whatever we think philosophically, I talk to those who think like me that should be informed by the current science we have. And science has a lot to say about causation right now. Now, where is the question? Why there is an issue about time direction? Because nature very clearly and very surprising, has shown us that in its fundamental laws does not know about a time direction. This has come out from Newton, has been confirmed by all the physics of the 18th, 19th, 20th, 21st centuries. All the fundamental physics we have tell us that the basic laws that we see in the universe don't distinguish past from future. Physicists tend to interpret law, I'll come back to that, just as regularities in nature and not as sort of governing or pushing or determining or anything like that, just as observation about regularity in nature. And the regularities observed are time reversal invariant. Let me spend just a few slides to make this clear. You often hear physicists talk about causation and often mentioning causation towards the future. But if you look in the detail, if you look in the books, for instance, in relativity, we say that if we know what happened at some time in a space-time diagram, this is time, this is space. If there is a time slice in which we know what happened, the basic equations tell us that from this knowledge, we can infer what happened in the causal domain of dependence. But if you look carefully, this is also the causal domain of invariance in the past, not just in the future. And whatever we say toward the past is toward the future. The same is true with light cones. In special relativity, we say that an event, if I change in the history of the world what happened in this point, necessarily something changes, but only in the future light cone. But if you take physics seriously, it's also true that it changes equally in the past light cone. There's nothing in elementary physics that distinguish the past and the future. This is also true about quantum mechanics. The paper copied here is the first paper who pointed this out, which is a little known, but I'm very attached to this paper, is by a guy known called Albert Einstein in 1931. This is also, there's been a lot of discussion. I've also written about that, but just for the sake of this discussion, just take the bottom line. Does quantum mechanics distinguishes the past from the future? The answer is no. Quantum mechanics add a level of uncertainty in our capacity of predicting, namely giving data in the present, we cannot determine the future univocally, but also the past. Given data in the present, we cannot determine the past univocally. There's the same uncertainty. So for a physicist, as I said, physicists tend to have an interpretation of laws just as expressing regularities. That's what, you know, you're taught in a university department of physics. Laws don't govern, don't compel, don't generate, don't produce. They just describe observed irregularities, which are very, very strong and very general, of course. And these laws are time reversal. And we do use a language of causing. For instance, this is a green ball which is not moving. The blue ball has a certain velocity, hits the green ball, and is the cause of the motion of the green ball after the event. But if you, this is only the language, because in the physics, the only thing you have is given masses, given position, a relation between the initial velocity v1, v2, and the final velocity w1, w2. And this relation is expressed by a law which goes in both equally in both directions. So if I play the actual motion ahead in time, I can describe this as the blue ball causing the motion of the green ball. If I play it back in time, I can cause it as the blue ball causing the green ball to stop. And so the cause and the effect are time reversed depending of how I run the time picture, showing that it seemed to be saying all this, that what we call cause and we call effect are just the two terms of something which is related by something, and just we use the name cause for the one that comes first, and we use the name effect for the one that comes later, without any other substantial difference between cause and effect, except this one. This is actually, let me give one more before jumping to the next point of discussion. Let me give you one more sort of rhetorical example. This is a round thing, it's a bomb. You use the equation of physics and you compute that, you know, if this is lighted, after a while there's a big explosion and a big, huge cloud. This is another round thing. So you use the equation of physics and you connect it to another big cloud, okay? Except that this is a bomb exploding, this is a sun being formed by the initial dust cloud that formed the solar system. So actual time goes from the bomb to the explosion here, from the exploded thing to the sun here. Once again, what causes what is not, does not seem to be a peculiarity of the phenomenon by itself, which one is a cause, which one is the first. It's just a fact of being ahead or later in what we call the direction of time. Now, let me jump to the sort of philosophical discussion about causes and effect. Physicists, of course, there's a deep influence from the classics, in particular Hume, famous discussion about causation. Hume is the first before or in parallel at the very beginning of the development of this physicist way of thinking of the world to reduce the notion of causation to just happening together. In fact, in the treatise, he gives a famous definition. I'm not going to read it, in which he says, basically, if you have something A and something B that always happen together, we just, this is what we mean by A causing B. And in this definition, you can reverse it in time. I mean, if you, the only distinction between A and B is that one is before and the other is later, nothing else. A little bit later, always in the treatise, he gives a second definition. The literature, Hume, it's a lot of discussion about the relation between these two definitions. I don't want to go at all. In which he talks about the idea that forms in our mind because of this repetition of having observed the connection between A and B. Of course, Hume is more precise. A and B are next to one another, and then there's other things like A and other things like B, things that resemble A, things that resemble B, that are in the same relation. We observe this many times, and says Hume, in our mind, this gives the impression that the two are necessarily related. So in the sense that seeing the first one gives us immediately the idea of the second. And this is even more strong in the inquiry, in which it says custom renders our experience useful to us and makes us expect for the future something that we observe being connected. So in these definitions here, it's something that happened in our mind, and it is in our mind that the expectation of the second, it's what orient, the effect is what we're expecting, while the cause is what we're aware of. So this is oriented, disoriented, while in nature is not. I could go more in detail, but I think I'm giving you the gist of that. And if a few centuries go by and things are not changed very much. If you take a recent philosopher, this is David Lewis, the most cited of the recent philosophers in the Stanford Encyclopedia. He gives a definition of causation, which I'm not going to read and go into the details. Also because it's not very good, it has been much criticized. I don't want to go into details, but it's essentially Hume one made much more precise, with probability instead of just many times happening together, and with the two, the causes effect not necessarily being contiguous to one another, because it could be a chain between one and another. But if you read carefully, the cause happened at time t, the effect happened at time t prime, but there's nothing that says which is which, unless the fact that we just assume that t is before t prime, and therefore we call cause the one that comes first. All this goes into the direction that in nature causes, the notion of causation doesn't play any role. The only thing that plays a role in nature is regularities between phenomenon that can be described by physical laws or by other laws in other sciences. And this is a position which is widespread among physicists, and at some point was preeminent in philosophy, and famously nobody put it more clearly and strongly than Bertrand Russell in a influential paper he wrote in 1913 about causation or causes, in which there is this celebrated sentence that says, the law of causality, I believe, like much of that passes muster among philosophers, sorry to the philosopher listening, but Russell was obviously a philosopher, is a relic of a bygone age, surviving like the monarchy, it was British of course, only because it is erroneously supposed to do no harm. So if you want to understand nature, forget about causes. It's just mythology, right? Nature, just things happen and they're related by laws, and there's nothing that causes anything. This is just our language that projects something funny on nature. Good. Now let me argue in the opposite direction right now, because as it has been observed repeatedly, we use causes and all together. And when Priya introduced this discussion, at some point she said the grand picture of the laws of physics that describe, causes and an effect in the universe. Priya is obviously a scientist, is an astrophysicist, always deep immersed in the scientific way of thinking. She naturally used the word causes and effect. And in fact, causes and effect, Pache, Russell are all over science. We talk about causes and effect all the time, right? It seems that what we're interested in science is causes. Isn't that what we ask all the time? What causes this? Why? What is the effect causes produced by this cause? Not only that, but in all the applied science, we're interested in causes, right? We want to know whether taking the vaccine causes a diminishing in the number of people dying or getting ill. So how do we put these things together? There is no oriented causation. There's nothing oriented in fundamental science. I take a sort of physicist position in which whatever happens supervenes on physics. Everything we're interested about the world is causation. Causes precede effect, and there's no orientation in nature. Something goes wrong here. There's a contradiction between these different assumptions. And nobody put this strongly and clearly like Nancy Cartwright, who has violently attacked, in fact, the Russell idea that causation plays no role in science, arguing that science is all about causal explanations. And she has a book whose title is Hunting Causes, etc. And that, in fact, this is what we're interested in. So the theoretical explanation, in the sense, the kind of explanation that Russell had in mind when he wrote these phrases, that's not science, in a sense, for Cartwright, because causal explanation, in her word, have some truth into them. And I disagree with Nancy on a number of things. One is her emphasis in the disunity of science. I think is either attacking a straw man, making too much of unity, or not seeing what has happened in the last century, which is a spectacular harmony and the disappearance of all the apparent contradiction between different sciences. And even more, I disagree with her, that's central to what I'm saying today, to her conclusion that precisely because in theoretical physics causes are absent, but are crucial to our understanding of the world, precisely for that theoretical physics is incomplete. I think this is just either naive or wrong, depending in which sense you take it. But she's completely right. She's obviously completely right that the ubiquity of a notion of cause in science, it's all over. Now, how do we come out of this confusion? Well, if you just look for a little bit of clarity, it's not so hard after all, because obviously eliminativism in foundations, which was what Russell was talking about, does not mean that we drop a notion. It only means that we do not trace this notion to the foundation. We trace it to something else. That can be contingent, particular, and can be very vast application, but not for this, it has to be thrown away like the monarchy, right? Only because, in fundamental physics, you never talk about cats. That doesn't mean that there are no cats, that cats is a bad idea, that we should forget about cats. Cats are cats. The world is full of cats. We can have a science about cats. Cats are great, even if they're not a part of fundamental physics. So the fact that causation cannot be read into fundamental physics, there's no reason for it to mean that we should eliminate from science, or that we make a mistake when we use in science. I think that there is a clean position that allows us to think that causation is it's ubiquitous. We use it everywhere, but it's not in the fundamental elementary laws of physics. And there are plenty of things which are not in the fundamental laws of physics, like cats, like the internet, like the sun. But nevertheless, supervene in an appropriate situation to the fundamental laws of physics. But this opens a question. So what do we trace causation to? And here I want to mention a recent development which had a lot of influence both in applications and on philosophical thinking about causation, which is mathematical modeling of causes itself. It's causal modeling has been developed by a number of people. Judea Perl was one of the most influential. He has a very influential books on the argument, in which he gives a picture, and an extraordinarily good picture of how do we use causes and what do we mean when we use causation. And I think this is the good entry point to separate the elementary law of physics where there's no causation from where, and try to tell us where causation come in the description of the world. So in great summary, this causal modeling function like that. In the universe, you have a lot of variables that describe what happened, but you select a smaller number of variables, say S, T, X, Y, W, Z. So some may say the number of people in a country, the number of people who get the COVID, those who get the vaccine, those who get to the hospital, those, etc., etc., etc. And then you assume you know some relations between these. This relation can be either because you know the law that connect them, some physical laws, some scientific laws, or because you have made some data. You have a large number of data, so you can do some frequency, you can interpret frequency probability. So you have a probability distribution over the values of these variables, of assignment of variables, values to these variables. Okay. From there, you deduce a causal relations as follows. First of all, you time all these variables. So these variables take value at some time, and you fix the time ordering of this. So this S comes before T and so on, and before W and so on. This is an input. And another input is that you assume that all the direction of causation are toward the future. And this is crucial. So it's an assumption that causation is toward the future. And then from the probabilities or from the laws, you deduce where you should put an arrow by using the notion of intervention. And the notion of intervention is defined in the next slide. It's as follows. Intervention is something that can happen, or you can do on the data, on a certain variable by doing the following thing, disregarding the relation between anything that come earlier in time and looking, according to the probabilities, according to the law that you know, what changes in the future if you change this variable. So for instance, Y change and W does not change. If you W in the future, then there's no arrow between T and W. And then you say that T causes a variation in T causes a variation in Y causes a variation in Z, and so on. And Perl has a theorem, in fact, that it's on the bottom of the slide here. If the variables are time indexes, so you have to time index a variable first. If you take some technical steps, then the probability distribution fixes the graph. So it tells you what is the cause of what. For instance, it tells you that, I don't know, the fact of having the vaccine by itself doesn't change the probability of getting close to somebody who has the COVID, but the fact of taking the vaccine diminishes the probability of getting the COVID, and so on and so on and so forth. So this captures the way we use causes in concrete. And I mean, there's been a debate between Perl and Cartwright if this is really capture all possible causation. Nancy Cartwright says no, but I think this is a finer details. She wants a larger notion of what we mean by causation. I think this is extremely wide because it does capture in science everything that we describe as this variable T affect this variable Y. Changing the variable T is a cause of changing the variable Y. And this uses the notion of intervention. So there's something intervening on the variable T. And the first thing you can think is that there's a human being here doing something at variable T. This is not in contradiction with the existence of laws, because remember, this is a subset of the variable of the universe. So there can be else in the universe, which you have disregarded. The laws you had is at fixed value of everything else. But if in everything else, something is not fixed, changed, for instance, a human doing something, then you can break the laws that you started from that connected these variables among themselves. And once you understand that, you understand that this manipulation, the intervention, does not need to be a human. It can be anything. And you can go to a more general notion of agency, much wider than a human. By agency, meaning anything, any phenomenon that acts on T, careful, and was not included in the set of laws that you had between these variables here. For instance, a meteorite falling from the sky and breaking something. This is an agent, because I have a description of what happened under certain condition. If something outside this condition, something external, comes in, this is an intervention by an agent. That's what I mean by agency, which is not necessarily human. So what is agency? It's a breaking of past causal links, which is possible in a approximate description, which did include something, so something else can come in. Okay? Causation, and I think this is the bottom line of this long discussion, makes sense if there is intervention and if there's agency. And it's precisely something in the time orientation of agency, which I haven't got to it yet, that gives the time orientation of causation. So if there's nothing, if we don't have an approximate description broken by an external agent, and if we don't think that the past is fixed, that it is the future that is going to be affected, there's no way of reducing causation to something understandable in physical terms. But every time we use causation in a way in science, which is understandable in terms of time, there is a set of relation which is approximate, something coming out from this relation, breaking the approximation, some exogenous agent, and an assumption that the past remains the same and the future changes. Good. Let me go to the second part and the key part of the talk. Now we have understood what is the role of the agent. And for the moment, let me think is a human. I mean, it can be also stone falling from the sky. The key point is that whatever is the agent, whether it's a stone falling from the sky or with a human or a machine, whatever, it's still a part of nature. It's not outside nature, right? Because I'm a naturalist. I don't believe that there are things outside nature. So I should be able to understand the agent which intervenes and allows us to think in terms of causes, why it, how it works, how it can keep the past fixed and affect the future. And that's where I want to bring in two key pieces of the puzzle, which I think glue the thing together. Namely, the physics of the agent and why the actual physics we have, which is time reversal invariant fundamentally, nevertheless allows the time orientation of the two key characteristics of this way of thinking, which is that the idea that the past is fixed and the future is open. Well, let me discuss these two points here separately. What makes the past fixed? Remember, the agent intervenes but does not change the past, only changes the future. And second, how can it change the future? Now, first, the past. The fact that the past is fixed is a common experience of all of us because the present is plenty of traces of the past. We have picture of the past, we have memories of the past. There are craters on the moon that witness for, stones falling on the moon in the past, not in the future. We have steps on the sun and so on and so forth. Is this in contradiction with what I've been preaching for the first 10 minutes, that fundamental physics is time reversal invariant? No, of course, because it's a microphysics, which is time reversal invariant, is the laws connecting a domain of variables when you don't disregard anything else. But the macrophysics of the world is obviously time oriented, right? The phenomena that we witness every day are irreversible. So the macro physics is irreversible, and we know why it is irreversible, because the fundamental law of time reversal invariant, but when you have a coarse-graining macroscopic description, this determines an entropy, and the individual solutions of the equation of motion that don't need to be time symmetric, so the behavior of the macroscopic variable can be irreversible if the entropy was low in some in one of the direction of time, the one we call the past. So the world is time oriented, but macroscopically, not microscopically. And for a long time, I've tried directly to connect the thermodynamic or macroscopic time orientation of the world irreversibility with the notion of agency, with the notion of causation, with the notion of fixity of the past and opening of the future, and I couldn't, because I think the key step which is needed is understand what are traces and in which sense agent open up the future. So let me go into that. Since traces are macroscopic phenomena, and since they're time-oriented, they can only time-oriented because microphysics is time-oriented, microphysics is time-oriented because of the second law of thermodynamics. So there should be a way of understanding how the second law of thermodynamics leads to traces. And it's possible to show, I'm not going into the physics, into the details, but let me give you the statement here, which is shown in a paper a few years ago of mine. If you have a thermodynamical system, which is composed by weakly interacting subsystems, so if there's a segregation of subsystem and they interact weakly, so it doesn't go directly to equilibrium, which is a normal situation of a universe. If initially is out of equilibrium, which is a situation of our universe, and if the thermalization times are long, so again, if each individual component takes a lot of time to equilibrate, then you can show that completely generically there are macroscopic traces. Namely, there are macroscopic configuration of the variables that from which you can deduce event in the past and not in the future. Not going to the, I've prepared some little model showing in a super simplified way how this happened. I'm not going into it, and I'm not going into the thermodynamics of the story because the audience is vast. I want just to give the main idea. But the main idea is that precisely because you start at low entropy, as time goes on, entropy grows. So you lose information in the growth of entropy, but a part of this information is captured, and you can see it concretely in mechanical models into the traces. So a memory has information about something, about an event. You can measure how much is this information, okay? And where does information come from? From the increase in entropy, or the decrease in negative entropy that happen along the thermalization. So memory is a physical mechanism which can be cleanly understood in terms of standard statistical mechanics and thermodynamics that transform low entropy into information. Okay? Agency. Once this is understood, agency is relatively simple. Because what is an agent? Again, is a system, is a physical system, so it obeys the laws of nature, such that it can take the same macroscopic past and split it in different macroscopic futures, okay? Since it is time-oriented, we are time-oriented, necessarily it's macroscopic. Namely, what we call by agent is a macroscopic description of a system. And being macroscopic, it's time-oriented by the second law of thermodynamics. It's an environment of low entropy, the entropy grows. So agency is an incomplete description. And notice that this matches exactly with the causal modeling description of what is the agency at the basis of the notion of causality. So it's an incomplete description. Let me jump to the picture here. if you have a macroscopic history of the world and a moment of time in which an agent can split between different macroscopic evolutions, you're not contradicting the determinism of the microphysics, because a macroscopic history is a large number of possible microphysics, one going up, one going straight, and one going down. So an agent is simply a system such that it has a dynamic, which we disregard in grand part, or which is not an agent anymore when we open it up and see what it is, that determines, according to which microstate was the system, the macrostate before, which one of the future happens. So it's something that decides whether going this way or this way. And this is not only permitted by elementary physics, but it's exactly what happened. And once again, the same model as before shows it's exactly what happened if the three conditions, I go back to the three conditions I had before, are satisfied. And namely, you need a global system composed by a subsystem, you need an initial thermodynamic at equilibrium and long thermalization times. Automatically, you get agency. Let me give you a sketch in this super simple model of what is going on here. You have two systems, a system with many little balls, which should describe thermodynamically, statistically, so you don't know the velocity of this ball. And then you have some macroscopic penduli moving. And if the interaction are very rare, once in a while, one of the little balls hit a big pendulum, so the big pendulum oscillates. Okay? If the initial distribution of energy is not in equilibrium between the two, what happens is that generically, energy goes from the little balls to the big balls. So when you see one ball oscillating, this is a memory of a previous hit, a previous exchange of energy between the two systems. Okay? But also, you can view the red system as a system, you don't know what's going on, but at some point it chooses to hit one or the other of these balls. So this is a minimal modeling of a system that chooses. And of course, this is nothing all that reading, the classical reading of agency, which you find, for instance, Spinoza, when famously Spinoza writes, men think themselves free because they're conscious of their choices and their desire, but they're ignorant of causes that incline them to want and choose, and thus never gives the faintest thought, even in their dreams, to those causes. This is not to say that men do not choose. They choose. That's exactly what they do. But by saying they choose, what we mean is that we're giving a macroscopic description of what goes on, in which the internal, what humans are, the brain or the body, splits the macroscopic evolution of the future. So memory and agency are physical mechanisms that transform low entropy into information. And by the way, I think this is the ultimate source of the information on which biology and culture build at large. And now we can bring everything together. How am I doing with time? Good. I'm getting to the end. I'll skip this. I'll come back maybe in a moment of that. The past is fixed because of traces. The future is open because the same macro past can evolve into different macro future. These are facts. These are facts which are generated thermodynamically by macroscopic description of system which is out of equilibrium, the system segregation, and thermalization. So therefore, the origin of the direction of causation is in the asymmetry of agency, which acts at some point influencing the future, and the presence of traces that allows us to consider the past fixed, to know about the past, okay? So it is because we are agents that have memory of the past and can split the future that we have the possibility of intervening in the sense of the causal modeling. The direction of time, it's in nature, is in the second law of thermodynamics, is not in us. We're not projecting something magic in our, we are governed by the second law of thermodynamics, which permits existence of traces. So nature has a direction of time in its macroscopical description. So nature is macroscopically time-oriented and microscopically non-time-oriented. This macroscopical orientation of the reversible phenomena, so all macroscopic phenomena, give rise to traces and to our possibility to split in the future. And in turn, we use this to read the causal relation between incomplete descriptions of nature in causal terms. So this is the full picture. And you see, it's a funny dance between subjective and objective, between special and general. There's no time orientation in the fundamental laws. We never describe all the degrees of freedom we describe macrophysics. It is a contingent fact, not imposed by law, but allowed by law, that this macroscopic description has past law entropy. Therefore, we're immersed in a world which is full of irreversible phenomena, time-oriented. These irreversible phenomena permit the existence of traces. So because of that, the past looks so fixed. The knowledge of the present gives us a huge amount of knowledge of the past and little knowledge of the future, much less knowledge of the future, and also precisely the same second law of thermodynamics allows certain physical system macroscopically to determine different macroscopic future for the same macroscopic past, so they're agents. And this is what we are. So we are agent that can split the future and consider the past fixed, and therefore we have a notion of manipulatability. We can do that. I can give the vaccine to people, and therefore people will heal. Okay, and because we have this strongly time-oriented notion of intervention, we think in terms of causation, which is what interests us, because after all, what we want to know is what happened if I do this and that. And this is the overall picture. Now, that's my rival point. Let me make two final comments before concluding, if I have a couple of minutes more. One, I've skipped one consideration here. This is a little bit of a side consideration, but Priya, you're interested in inference in general, and I think I should not avoid mentioning this. At the light of everything I said, this is something that always fascinated me. Inference implications is in pure logic, of course, and by itself has nothing to do with time, right? If you say all humans are mortal, Socrates is a human, and therefore Socrates is mortal, this is not after time. This is not after that in time. Logic is outside time. If I say little a is the set A and set A is the subset B, therefore little a set B, this is not after. So this lives outside time, but nevertheless, we use a temporal language for talking about logical implication. Why do we? There's something funny here. We use a temporal language because in our thinking, we walk through the logical atemporal world in time. And of course, if you want to think about the consequence of some premises, we have to hold the premises in our memory. And we can only remember the past. We cannot remember the future. So there is a very peculiar, you see, there is a very peculiar game here. It's not what I was talking about, because I was talking about causation in physical world. This is not about the physical world. But there is something remarkably similar in the relation between that atemporal world, the logic, and the way our own thinking deals with, if you want to believe, there is a temporal world of logic, which is always in time. But why it is in time? Because of specific physics of our brain, which works thanks to remember the past, thanks to traces, and being open. You know, when we write premises, it's like we don't yet know what is a possible the possible conclusion, the possible thesis, and so this is the correct one among others. So once again, I think it's very important to disentangle the kind of relations which don't depend on the peculiar orientation in time of our way of thinking because of what we are as a macroscopic physical being in the second law of thermodynamics, from the one that depend on that. Now, the last comment has to do with this macroscopic approximation here. So if you notice, I left a hole here, and this is an idea which I want to mention just to complete this picture here. It's perfectly okay to say that the macro variables are whatever they are. And the fact that entropy was low in the past is just a contingent fact of nature. Or as David Albert wants to say, it's also law of nature. Let's call it the law of nature. And then we have a law saying that the past is special. But there's another possibility, which I find far more interesting, which is the following. When we say that entropy was low in the past, we should remember what entropy is. Entropy depends on two things, the state of the universe and the macroscopic variables that we use. Now, the macroscopic variables are not arbitrarily chosen. They are determined by the physical interaction between a system and another system. So if S is a universe and O is a subset, O interact with S through not all the variables of the universe, but through a finite number of variables, A1, AN. And the entropy is a number of microstates corresponding to given values of this finite number of variables. So in other words, the macroscopic variables are determined by the system with respect to which entropy is defined. It's wrong to say that a system by itself has an entropy. A system has an entropy only if you say with respect to which system is interacting or with respect to which variable you're measuring this entropy. But this opens an obvious possibility that if the entropy universe was low in the past, it's not the state that was special, it's the subsystem that determines special macroscopic variables. So low entropy may mean not there is something non-generic in the microstate of the universe, but there is something non-generic in the subsystem with respect to which, or from the perspective of which you're looking at the universe. And this second possibility makes much more sense to me. And if so, and this is my last slide, the macroscopic approximation from which the very orientation of time, the second law of thermodynamics, is determined, is also perspectival. Is not subjective in the sense that it's arbitrary in any sense. It's perspectival in the same sense in which the rotation of the sky that we see around us is perspectival. It's not a subjective effect. It's true. The sun rotates. There's a sunset and sunrise. But we don't understand it by looking at the sky, at the stars, at the moon. We understand it looking at the relation between the stone on which rotating on which we sit and the rest of the universe. So I think that also the second law of thermodynamics should be understood in a similar way, namely as a relation of a set of variables in terms of which we exist as macroscopic objects, which are special, and are special in the sense that with respect to those, the entropy of the universe was the past. And why they're special? Well, because otherwise we wouldn't have been. I mean, we are being in time. That's what we are. Biology is a process in time that can only happen in a set of macroscopic variables with respect to which there's a second law of thermodynamics. And therefore can only happen in a subset of macroscopic variables, which has a property of being related to the rest of the universe in a way that determines a low entropy. So I've put a question mark here because this is an idea which I'm fascinating, but it's bold and courageous. The rest, I'm much, so you can bracket that. The rest, I'm ready to defend against criticism. Of course, if figures are strong enough, I'll change my mind. So bracketing that, causation is time-oriented, definitely. Why? Because when we talk about causation, we are always talking about intervention. So if I do that, or if something does that, something happened in the past. And the notion of intervention requires something exogenous, something external. So we are talking about a set of phenomena which we understand by themselves, but we also assume that something can happen from the outside. And we assume that whatever the situation, we know what was in the past, and we don't know what is the future. And why we make this assumption, not because we are, time-oriented extranatural beings, but because we are macroscopic phenomena in a macroscopic time-oriented description of the universe. And it can be shown that the second law of thermodynamics generates the existence of traces, allows the existence of agency. But importantly, is not the second law of thermodynamics that has anything to do with causation by itself at all. If anything, second law of thermodynamics destroys information, doesn't produce it, doesn't allow to predict anything, allows us to lose information. What the second law of thermodynamics plus system segregation plus law thermalization times allows to is traces and agency. And this is the basis that generates our very peculiar description of the world in terms of intervention, which ground the notion of causation. So causality is not in nature by itself, is not a fundamental way for understanding nature, but is an ubiquitous, extraordinary, general way we have as agent for interacting with approximate description of the world, where we actually can act on some moment, knowing the past and having the future open. And this is it. Thank you very much.
Thank you so much, Carlo. That was really, really amazing. So I'm going to request everyone to clap virtually to express our thanks. This was a brilliant dissection of cause and effect. And I'm particularly interested in how nicely you clarified this role of the second law of thermodynamics, which is often like really invoked to account for the existence of an arrow of time itself. And I think you kind of very nicely clarified why it is that you arrive at the notion of an arrow. And that has a lot more to do with the tracers than it does with the actual content of the law or the predictions of the law. So before I open up to questions, I wanted to ask a sort of a quick question myself. And that really has to do, I mean, it is this sort of deeper question about, do you think it is our own sense of biological time and the degeneration that goes with it? There's a degeneration and a lifetime that goes with it. So that has a fundamental impact. And I think you discussed this briefly in your book, right, in Order of Time, that this sort of rhythms are set by these very, very random events, right? So, and therefore, if we had been sentient beings with no lifetime at all, then the way in which you would order things might look completely different, right? I mean,
yes, I do. I definitely do think so. Somehow the overall idea behind the book, the Order of Time, is that a lot of confusion we make about the notion of time because we are mixing up different notions. We're missing out different levels of what time is. As you said, opening the series, we need to disentangle, and we get clarity by disentangling. So we tend to say time is this, time is that, but time is a lot of things. And there is an experiential time, there's a psychological time, there is a time of the clock, there is a time variable in generativity. These are all somehow related to one another, obviously, but they're very different layers. So when you mention the sense of the, you said the biological and the degeneracy of time, this, what we perceive experientially of the passing of time, it has to do not directly with the clock time, because that's not what we are. Our perception is something much more complicated. We're perceiving well more complex layer of phenomena. one silly way of putting this is that we remember time because we know time because we remember a moment ago, and a clock doesn't remember a moment ago, right? A clock has no memory. So a clock doesn't have the same sense of time of us. Obviously, even if it had a sense, it couldn't have a sense. So we should take apart the various pieces of time. And when we say this aspect of time comes because of the way our brain works, it does not mean that, okay, so this is what time is, nothing else, because a clock is still a clock and measure a variable that we can legitimately call time. Just we shouldn't use the same word so cavaliering without realizing that it means different things.
Right. And you know, and as you mentioned, a lot of this wanting to order cause and effect in time has to do with the need to make predictions, right? For you know, probabilities or of occurrence of future events.
Yes. And exactly, it has to do with the need of making predictions, qualified, because there is a sense in which we can make prediction equally toward the future, toward the past, right? We figure out the solar system dynamics. Solar system is a very controllable system, is an almost perfect physical dynamical system, which and so we can measure the position of velocity on Venus, Mars, Jupiter, everything, and make great prediction to the future and to the past equally. There's no difference in a sense.
Right.
However,
this is where I was going to just interject the word. I mean, determinism, right? The fact that it's a deterministic system without chaos and uncertainty that is
exactly
right into it, right? Okay.
Exactly. And to the extent in which there is uncertainty, okay, and to the extent in which we have a system which is open to external something else, we have also different kind of questioning, which is not just and the other question is what happened if, okay, and I can also ask it for the solar system. No, what happened if a meteorite come in? And that's also I can do in the past and in the future. For instance, suppose I compute there was an eclipse at the time of a battle of, between in the Mahabharata, between the Pandava and the mentioned eclipses, and I want to compute when it was. And then somebody says, well, wait a moment, what happened if in between there was an asteroid going by and the moon has a little bit accelerated? So what happened if it can work in the past and in the future? But we are interested in a very specific what happened if. What happened if I do something and I know the past?
Right.
And that's what causation is.
Right.
Causation is if I say hi, what are you going to answer? Okay, I remember what happened before, but I can interject something here. I want to know what happened in the future. And that's when causation comes in. And we're using this logic to understand nature. Yeah. It's powerful logic, but it's a sort of high-level logic. It's not a low-level logic in the way nature works.
And that we need to make all these discriminations about the system, the subsystem, about also which part of the past is fixed. If you take the past as fixed, then it's a dynamic view versus a passive view of the past. Right? So you can have both a dynamic and a passive view of the past, and that depends on the system and the subsystem in question. Okay, so I will not hog you, and I will ask the first question. Peter Morgan, who actually works on the nature of quantum mechanics here at Yale. So his question was, without disagreeing with much of what you've said, Carlo, the past is only fixed insofar as traces persist. Is it only that the creation of traces is relatively fast and the decay of traces is slower? If we burn the evidence, it is gone.
Yes, my answer is yes. And to me, it has been a long path to accept this idea, but I am pretty convinced now. So there's nothing else that makes the past fixed beside the fact, the natural fact that because of the second law of thermodynamics, we have a huge amount of traces of the past, macroscopic traces of the past. So we have a great amount of information about the past we don't have about the future. I don't think there is anything else. And Peter works in quantum mechanics. It's a long and subtle discussion how this plays off in quantum theory, because the usual presentation of quantum theory in textbook is I make a preparation and then I make a measurement in the future. So it seems to be an arrow time seems to be in the textbook in the presentation of the theory, but I think this is just a presentation thing. I could, I could make a series of measurement, and then I can ask, if I know this, what do I know about the previous and the past one? And so I think it would be the same in quantum mechanics. So the way he put it in, I just read in the chat, I would stand with it. It's existence of traces that give us the fixity of the past, and the existence of traces is rooted in the second law of thermodynamics, which in turn is rooted in past law entropy.
So the next question is from Shyam Sundar, who is a faculty in the School of Management. And his question is, if nature could be partitioned into one micro and one macro layer, then no direction at micro and direction at macro argument simply would not work. But if nature consists of an arbitrary number of layers in micro and macro state hierarchies, then this reversal between adjacent layers of hierarchy would not work. How would it work in 3 or more layers? How would it work?
Yeah, I was reading through. So it says it would work if it is in 2. What about if it is in more? I take note and I'll think about. I don't think I can answer immediately, but it might be. I don't know if this is a question that has an obvious and immediate answer or not. Maybe not. I think I need to think about that.
Okay. There's a question from Rohit Parekh, who's asking, if 2 people observing the same traces make different inferences about the past, we assume that one is right and the other is wrong, or both are wrong, but perhaps there is no fact of the matter as to how the past was. Then the past, just like the future, is a fan of possibilities. I'm not suggesting this, but pointing it out as one way to look at things. I think this is sort of what I was alluding to as well, about dynamic past versus passive past.
Yes, and there is something disconcerting in that. I think the actual answer depends whether you fold quantum mechanics in or not. So if h bar was 0, if the world was not quantum mechanical, we could make a fantasy story, sort of forgetting excessive chaos, and say, well, the history of the world is the history of the world, period. But then it will be equal to the future. I mean, it's just one history of the world, is the past and the future. But we know that there is, at least what we have access to the world is probabilistic because of quantum mechanics and chaos and everything else. And this is what definitely makes the future open. But I believe strongly that it equally makes the past open. So the past is undetermined. And what we mean by the determination of the past is precisely the existence of traces. So macroscopically is determined. I mean, we have I can take a movie, and then later on I look at the movie and say, look, this is a hard proof of what happened. But macroscopically, I cannot do this quantum mechanically.
So the next question is from Nicholas Gall. So is the concept of agency and the derivative concept of causation merely a form of stance in the sense of stance described by Dennett? Example, an agential stance is a stance like intentional stance. All such stances merely give us more fruitful explanatory and predictive power. Even more generally, Albert's past hypothesis of low entropy is also another stance, one that is fruitful for our macroscopic purposes.
I don't know. I don't know. It's a deep question. I tend to answer no. I mean, tend to answer, but I'm not completely sure. My first reaction, I should copy all these chats and think about them later. My immediate reaction would be to say that no, we actually, as subsystem, I mean, since we just de facto interact with the world through some variables, de facto we have a macroscopic description. So de facto there are traces. So de facto there is agency. So it's just a description of what is going on. So causation ultimately is a description of what is going on, but not at the fundamental level. After, it's like, it's a description of what is going on, that in my car, if I push the accelerator, it goes faster. There's nothing fundamental here. It's a story about what actually is, but it's not a stance. It's just, what it is. It seems to me that this is the case, but I might be wrong here, and maybe it's just a choice of a perspective. So I'll think more carefully about this question.
So the next question is from computer scientist and philosopher Brian Cantwell Smith, who is part of our series and will be speaking later on. He asks, I hear you saying that biology and culture require low entropy macroscopic variables. So that is how, why, where we developed. Could it instead be that we are more responsible for the low entropy macroscopic properties we use rather than as a consequence of them? For example, could it be that we human coarse grain the world in ways that parcel it up in low entropy ways and restrict the ways in which we find it intelligible, including, I would say, establishing object identity to those that allow us to think and imagine?
Great question. I would not think that the two alternatives are alternatives. Mm-hmm. I think it seemed to me that the second is very likely a convincing story of what happens in our relation with the world, and is not alternative to the first, because to play out the second, we need a lot of previous information to start with. And so what I was talking about is not, when I said, I mean, I forgot his name. Can you repeat his name?
Brian Cantwell Smith.
Ryan, thank you, Ryan. I'm happy he picked up this. For me, it's an idea that hit me very strongly. Biology works with information, and culture works with information. Where does information come from? In a sense, there's a sense in which you cannot create information from nothing. In some sense, where does it come from? And if it is true, I mean, agency create information, right? I decided to go right or left, so there was no bit. Now there's one bit of information. I've gone right, left, and traces are information. I mean, a picture gives me information about the past in all possible senses of information. Where does it come from? From the perspective of a physicist. So for a physicist, imagine the world is just a little stone bouncing around. Where is information, or a quantum state or whatever? It's not in the microphysics, it's in the macrophysics, and it's sourced by the negative entropy to start from, okay? So this is what gives the raw material of information. That's what biology can work with, culture can work with. But then the way we deal with information is extraordinarily complicated, complex. It's certainly not just making memories and making choices. We do all sorts of stuff with information, right? We talk, think, write books, do computers and everything. And the way we then interact with the world to capture other information is very complex. And I'm a physicist, I'm not at all going into this complexity. And the fact that we are actively filtering out, as Ray is saying, it's it's a perspective that seems very credible to me, and I don't see in contradiction with what my sort of the underlying generation of raw information from past low entropy.
Great. So we have a question from Jenny Wagner. Is the definition of entropy in the second law of thermodynamics unique? Could there possibly be a definition of entropy which was high in the past?
Yes, I think it's not unique. And I think there could be a definition of entropy that was high in the past. And I have let me give you two little examples. One is actually from physics. I mean, if I take the air in this room, I say, well, it's just some molecules, and the pressure and the volume, temperature, and I'm a physicist, I can write down, I know the volume, the pressure, I can compute the entropy. Here's the entropy, it's a number, joule or whatever. But now say, oh, wait a minute, I also have, I also can measure, not only I have a thermometer and a pressure meter and a meter for the volume, I also have a device that computes the relative amount of oxygen and nitrogen. Okay, so I can measure that. So now I have one more device. So now I have to redo the calculation of entropy. It's a different entropy. It's lower. So entropy depends of how interact. And can it be higher in the past and lower in the past? Yes. Here is an example. I have a box with some balls bouncing around. Okay, I take a movie, and the balls are in some position, and then some end of time, and then they move in some other position, some end of time. And you look at them and you say, well, I don't know, the entropy seems to be the same on both. But I said, oh, no, sorry, I showed you the movie with a filter. Let me take away the filter. And you see that originally all the yellow movie were one side, or the blue were on the other side, one end of time. So they mix it up. I say, oh, I can do an easy entropy calculation, you know, my macroscopic thing, how many yellow are on the left. And clearly the entropy went up because it all mixed. And then say, oh, wait. There's another filter, in fact. And the other filter shows that, in fact, not only the balls were yellow and blue, but they also were, you know, some with a little bump and some with a little, some other properties. And in fact, you do a calculation with this property and you define that the entropy was lower than the other side. So you can make it up, stories in which entropy can be in one direction or the other direction, depending on the macroscopic variable that you use, which depending on how you look at them, so depending on your own interaction with them. So it's not subjective. It depends on the actual interaction Hamiltonian between the system and the other system, the physical system, with respect to which entropy is defined.
Great. So we have the final two questions. So we have Darcia, who is asking, what is your interpretation of retrocausality?
Well, retrocausality is used in various contexts. Was used in quantum mechanics. For instance, Hugh Price, in the last chapter of his book, talks about retrocausality. There is sort of the group of physicists in Israel around Aronoff that thinks about retrocausality. I don't know if this is what the specific use of retrocausality. There are contexts in which it seems natural to use the notion of cause in reverse. As I've argued, the notion of cause is not primitive. It's a complicated story that we have because we assume that we can intervene at some point at fixed past. And then we want to know what happened according to the law of physics or according to our information about the future. So nothing prevents us to play the opposite game. It just sounds unintuitive to us because that's not the usual intuition. But I gave you an example in my talk about retrocausality. If I want to say, look, I have my computer simulation of what happened to the solar system in the past, and I see that there is not just a solar system, to our region of the galaxy in the past, I see some clouds. And I say, oh, this is a cloud that is caused by the sun in the future. This is the sun that is caused by Andromeda in the future. That's retrocausality. We're just reading out in a different way some objective relation between, in that case, objective relations, because that's classical, between the position of matter in the galaxy in our region. It doesn't make sense because we don't think in terms of intervention toward the past, because we cannot intervene in the past because there's second law of thermodynamics. But there's nothing intuitively contradictory in it.
I think there are 2 more questions. Are you game to go? Keep going. Okay.
I'm happy to answer. These questions are great.
Yeah, we'll give you that.
I want to save the chat because I want to think about all of them.
We'll take care of that to save it and edit and send to you. So Petter has the question: does the trace question lead to the identity question? If there's no identity, are there no traces?
I don't know which identity he means in that. You mean identity? Identity of objects, identity of people. What is identity being?
I don't know. I think we can ask him to type while we get that clarified. I can move on.
Maybe I can answer generically. Let me take identity in the sense of permanence versus in the sense in which this pen is the same pen 1 minute before, 1 minute later. So this is the identity of the pen. As a physicist, I interpret identity across time just as similarity that similarity between a process to repeat itself. So in a sense, yes, we identify object because we recognize something we call an object now with something about which we have the traces, and much more strongly, I think that the sense of identity personally we have as ourselves is deeply, deeply rooted in the fact that we have memories. So we have a story about ourselves, and this is what we are. What I am is the ensemble of things I remember, and I tell a narration about myself. So traces are, in all sense, ingredients for memories, both at the level of personal identity and object identity.
I had the clarification, which is in the sense of differentiation.
Right. So
I think the pen example is a good one. So
yeah. So I think of the world as an ensemble of events, processes, which are punctual or short in time. So it's these traces, what glues different events to make an object, and you different objects by using the information that you have about them in the past. That's the way I think. That seemed to me a natural way we can think, especially at the light of quantum field theory, and the way physics describe the world today, which is not objects, it's more processes, more events. So
the final question before we wrap up, and it's from Paul Grimstad. He has a comment about Hume and cause. So Hume's skepticism about induction was premised on the idea that we never have an experience of the cause as such. All we have are the regularities, the constant conjunction of one thing following another. In such a picture, one cannot rationally justify predictions about what will happen in the future because you cannot assume the future will resemble the past. And further, you cannot assume induction itself will continue to function, stably as it had in the past. What does it mean to locate or see causal power itself for physics and thus get beyond Hume's skepticism that the idea of causal power was just a piece of metaphysics that does not actually describe anything in nature?
Fantastic.
It's a fantastic question, yes.
No, yeah, fantastic question, because let me answer as a physicist. The answer is no. I mean, for a physicist, you don't go beyond Hume at all. I mean, you don't want to go beyond Hume. There is no causation beyond the regularities and induction. And of induction, of course, we know that it fails, right? You know the famous Russell Turkey inductionist, who every morning the peasant give him food, so he make a law of nature that every morning the peasant is come to go bring food until the morning the peasant comes in and kill the turkey. So induction fails. We know that induction fails, but that's it. We know that the world of physics fail exactly in the same sense. It's exactly like Russell Turkey. Newton law failed. Generativity is going to fail now. We don't know, and this could be a good question for a physicist, why induction fails so little. I don't have an answer to that as a scientist. I don't know an answer in philosophy. I don't find convincing any answer that tries to ground causation or laws or anything else in something beyond regularity, precisely because induction fails. So the answer to this great question, the question, it's what allows a scientist to go beyond Hume's skepticism about causation, which is a skepticism about the reliability of induction, and the answer is nothing at all. I don't want to go beyond that. I want to keep the serene skepticism. And of course, Hume never said that because of that you should not expect the sun to rise tomorrow. You should expect the sun rise tomorrow, right? Because induction works very well. But you're not certain that the sun will rise tomorrow. And are we certain that the sun is right tomorrow? Of course we're not.
Right. But I mean, isn't this also tied to the fact that we call something a law precisely when it is stable? It has to be, so the regularity of the law is that it has stable explanatory power. And just as you said very nicely with the sun example, we know that we have a very high chance of expecting that the sun will rise tomorrow. But is there a guarantee? No.
Yes, exactly. And I think that there is a confusion, a recurring confusion in philosophy. There was a recent talk by John Norton on the notion of possibility, where he had a great rhetorical attack to the notion of possibility defined as everything is possible, which is not logically impossible. I was very sympathetic with him. We don't use possibility in that sense in our daily life, and we don't use possibility in that sense in science. Lack of certainty doesn't mean lack of knowledge.
Right.
That's a key point.
Yeah.
What am I certain about? Zero. Okay. What I have knowledge about? A huge amount of things. I know that my name is Carlo. I know that this is a computer. I know that the Earth is spherical. What am I certain about? Nothing. So the lack of certainty, which is the lack of a guarantee to the absolute solidity of our it doesn't exist, but this doesn't take away any of the reliability of the knowledge we have, including the reliability of the Maxwell equations in their domain application and so on and so forth. So I think that we can be Humean in this sense with respect to causation. And we can be Humean from the fundamental level with respect to the laws of physics, just expressing regularity. It's just an extrapolation, and rely on the fact that by induction, once again, we have seen how stable are this kind of regularity that we find, without for this reason asking philosophy to find an extra reason for giving us a certainty, which if we had, it would be nefarious, because it would block us from being open to the possibility that there is something else going on that we could understand better.
Great. So thank you very much, Carlo, for this wonderful talk and real clear explanations, and for helping us sort out some very thorny issues about which we have a lot of misconceptions. And as you said, a lot of it has to do with the nuances of meaning and of using words that don't mean the same thing in many different contexts. So before I thank you, let me just advertise the continuing conversation that is going to happen tomorrow. So we have at the same time at 3 p.m. tomorrow with the same Zoom link that you used today. You can come for a follow-up discussion with Eric Winsberg, and we'll just delve a little bit deeper into, and we had some excellent questions, and I'm sure that a lot of these directions will be explored in much more detail. And before I leave, I just wanted to flash to you this website for our project and the list of speakers, upcoming speakers over the year. So it's a monthly colloquium series and follow-up discussion. So please come and attend those. And so I want to thank everyone for coming today and participating. And Carlo, delighted. We would have been much more excited, of course, if we had all met in person. We would have had a very nice reception and lovely food and wine after this in one of those beautiful sort of old Yale buildings. But till then, till next time, till that happens, we are delighted that you were able to take the time to join us today.
It will happen in the future. Thank you very much for everything. It was wonderful, and we were far away, which perhaps allowed more people to come. So, which was very good, and I'm very grateful. And thank you for this, especially this extraordinary set of questions at the end that will make me think for a while.
Thank you very much. Bye, bye everyone, and see you all tomorrow. Bye, ciao.